to introduce you.
How are things at the University of Tabriz? Are students coming in and things?
Only the PhD students come to the university, and but other students like graduate student and undergraduate classes and meetings are online.
I see.
But our situation in pandemic is very good now, and I hope this situation continues in future.
That's very good to hear. I hope so too.
What about your
we are
university? Everything is online or not?
Yeah, no, we are open. Most of our classes are in person, graduate and undergraduate, all of them. We are now approaching the end of the semester. Actually, this week is the exam week already. I teach a graduate class now. It is in person. We'll see what's going to happen in the next semester. But for now, it's all in person.
I see. It's very good. In our country, the vaccine injection rate is great. So the next semester will be present.
That's great.
Thank you. And I'm proud to accept our invitation, and I'm so glad to see you here. You can start if you want.
Thank you very much. Thanks for inviting, for organizing the conference. I'm very glad to see you all either on your screens or by your names. And I also apologize that I wasn't able to attend other talks, but this is a very tough time. We have exam week, as I was mentioning, and the schedule is a little bit messed up. So my apologies for that. Thank you for the opportunity. I will talk about massive gravity. I will have less to say about black holes, not because this is not interesting. It's actually a very interesting subject in massive gravity, but my talk is more basic, perhaps trying to extend massive gravity into a theory which may have better behavior. And then obviously we can look for black holes and cosmologies, as actually many of you have been looking in some of the extensions I'll talk about. Let me begin with some motivation. I know this is not really necessary for many of you because you've worked on this subject, but there are also people who may not be familiar. So there are some ambitious questions that massive gravity or bigravity, which is straightforward extension of massive gravity, would like to address. And first and foremost, that's the question of late time accelerated expansion of the universe. Typically, we parameterize that expansion by a cosmological constant or a quintessence field. In both cases, the parameterization is in a very good agreement, or can be made in a good agreement with observations. But there are fundamental questions that remain as to why you would put such a small cosmological constant, and that putting such a small cosmological constant is not technically natural from the point of view of quantum field theory, because that's the operator in your Lagrangian, which gets quadratic renormalizations and is sensitive to very high energy physics, and therefore it requires very high level of high degree of fine tuning. As opposed to that, in massive gravity, we also put a small parameter, which is a graviton mass. However, that parameter has only renormalizations which are proportional to itself. Therefore, the theory warrants that the smallness of the parameter will be retained throughout the renormalization procedure, unlike in the cosmological constant case. There are other possible applications, equally interesting and equally important. Some people verged into understanding or using pi gravity, perhaps to look at the alternative early universe scenario, such as alternatives to inflation. In this context, they've used very much such things as Galileons or Galileons combined with some other theories, which open interesting opportunities for the early universe. And I won't be talking about that because of the lack of time, obviously. And then there is also a very long-standing puzzle. Many of you are well aware of that, and that's the old cosmological constant problem, which is as to why why the curvature that explains accelerated expansion of the universe today is so small as compared to what quantum mechanics put together with particle theory would typically estimate or give you a rough idea as to what it has to be. So the number that we see is a lot smaller than that. So this is by itself a separate subject related to massive gravity, of course. And again, I won't have much to say about this in this talk. Now, the language that I will be using here is the language of the degrees of freedom. And there is a specific reason as to why, because it's easiest to see in that language potential issues and then potential resolutions of those issues. In general relativity, we don't necessarily use that language, at least from the beginning. We use the language of curvature, but in this case, it's easier to use that language. And most of the time, I'll be talking about expansion around flat space. And that's not because we're not interested in other backgrounds. Obviously, our main interest is in cosmology and in black holes and so on and so forth. But flat space, in the context in which I'm discussing, is one of the problematic spaces, in fact, because the strong coupling problem manifests the strongest in a flat space, and also the what's called the Van Dam-Zakharov discontinuity is also manifesting in the most clearest way in flat space. In some ways, it's the worst case scenario, and therefore we'd like to address this in the worst case scenario so that everything else would be even better. So in curved backgrounds, these problems are somewhat mitigated, as you know, or even resolved. And many of you know that the Weinstein mechanism of resolving the vDVZ discontinuity problem is entirely based on the background and how the background resolves that problem. So, but we're looking for other mechanisms which would be simpler, calculable, perhaps perturbatively, because in the case of Weinstein mechanism, you have to resort to non-perturbative calculations in the Newton's constant after you found your background. All right, so the next few slides will be just motivational. And as I said, talking about degrees of freedom. And I will be beginning with comparing to massive gauge fields. Photon, as far as we know, is massless to a great accuracy. But if you have photon electromagnetic waves propagating in some medium, then they acquire a mass. As you know, in plasma, there is a the photon becomes massive. In superconductors, as you know, photon is massive. That's just Meissner effect. And if you have any type of charge condensate, any condensate BEC, which is charged, which is close to superconductors, may not be exactly superconductors, still photon will be massive. More general picture of that is, of course, the Higgs mechanism that we all know well in our universe. And we know that because the Higgs is present in our universe, our whole universe is permeated by this Higgs web, and it gives mass to the W and Z gauge bosons. But in all these cases, the point that I would like to make is that in all these cases, in addition to the longitudinal components of the massive gauge fields, there are additional degrees of freedom. So what I mean is this. A massive photon has to have 3 degrees of freedom. So that is dictated by actually the Poincare group, Poincare symmetry. And you always have that at short distances, whether you take a material or not. And so you would expect to have perhaps a theory with just 3 degrees of freedom. But typically, when photon becomes massive, for some mechanisms like the ones outlined here, you also get additional modes, such as in plasma, I mentioned, for instance, in addition to the longitudinal mode of a massive photon, you get what's called the ion acoustic waves. In superconductors, obviously, you have phonons. And in the Higgs mechanism, you have the Higgs boson itself, the radial Higgs boson itself, which is not the longitudinal mode of the massive gauge boson. So massive, the W's and Z's are already massive, and then in addition, you have the one more scalar field. So this seems to be important for understanding of this phenomena and these theories at distances shorter than typical scales described by these theories, or in terms of high energy physics, this seems to be important for good and perturbative high energy behavior of all these theories, so that the theory becomes calculable at energies above the one at which typically it would become strongly coupled. So this would be the motivation for me, in particular, to look for additional degrees of freedom on top of the 5 degrees of freedom of a massive graviton. Obviously, we want healthy degrees of freedom, which potentially could raise higher or even resolve the strong coupling behavior of massive gravity. So to elaborate on this point in more precisely, for instance, if you take SU2 non-abelian massive gauge field and you don't use the Higgs mechanism, you just write down the mass term by hands in the Lagrangian, as it was done, in 1961 or 62 by Glashow, you can look at the longitudinal components of those massive gauge fields. There are 3 of them. They are in adjoint representation of SU2. There are 3 of them, and therefore there are 3 longitudinal modes, which are denoted by pi with an index A. A runs 1, 2, 3. And you can zoom onto that sector, because that's the sector which becomes strongly coupled at high energy scale as you approach that scale, which is mass divided by the coupling constant. And the Lagrangian that you get is the one that you see here. There is a kinetic term, but that kinetic term is multiplied by some nonlinear function of the fields, which means that if you were to develop perturbation theory for these fields, for scattering, you would have a strongly coupled behavior at scale V. For instance, when you expand this, let's say you expand in the quartic order, you would have a term which is d pi times pi squared divided by v squared, and that's a 4 particle amplitude, which for sure will become strong at scale V. So that's very typical when you don't introduce Higgs mechanism and write down the mass by hand. And that is exactly the issue that is resolved by the Higgs particle, because Higgs particle cancels out those diagrams and makes the theory calculable to high energies. So in pure massive gravity, very similar thing is happening in the consistent theory of massive gravity formulated by these authors. And similar thing is happening in brain-induced gravity as well. Now, classically, that seems to be tolerable because there is the Einstein mechanism which enables you to do classical calculations and screen these additional degrees of freedom from the domains in which they are physically observable, or leave very small trace of those effects. But in the end, we would like to have, of course, quantized effective field theory for massive gravity, like we can have it for general relativity. And in that context, perturbatively, we always encounter this problem of the strong coupling behavior at a scale, which is the scale λ3. So I would like to go a little bit in details of the origin of that scale. It's well known, but maybe not emphasized enough. And then from that perspective, I will propose a different type of solution for that issue by extending theory of massive gravity, or rather embedding that theory into a bigger theory. So the issue is very simple to see. On the Minkowski space, you expand massive gravity and you keep only the leading pieces in the mass. So here I've neglected the next to leading pieces in the graviton mass. This is a schematic way of writing of the quadratic form, the Einstein-Hilbert quadratic form. This is the full-fledged, all the indices contracted, and so on and so forth. The key point is that it's got one derivative and one power of the field squared. H is a small perturbation of a gravitational field about Minkowski space. And then the pi is the longitudinal mode of that field in massive gravity, and you necessarily get this term, which is a mixing of H with two derivatives of pi. There are indices here. This structure is transverse, which is not shown on my slide, but it is transverse, so that in this approximation, the theory has linear diffeomorphisms. And as you see, this pi mode doesn't have the kinetic term unless you diagonalize, and when you diagonalize, you get the kinetic term, which is now proportional to the fourth power of the mass. And as a result, it also couples to the stress tensor now after the diagonalization. And then to normalize canonically, this pi field, you rescale it. So you get the Lagrangian for the tensor mode, the Lagrangian for the scalar mode with a right sign. I'm using here mostly plus signature, so this is a right sign for the scalar kinetic term. And then you have coupling of the tensor to the stress tensor and the pi to the stress tensor with equal strengths, because this m gets removed after the rescaling. So far so good, except that you get extra contribution to your gravity of order 1 as compared to the tensor contribution, and this is the origin of the vDVZ discontinuity, as you know. But in addition, you also get, in the nonlinear terms, which I didn't keep track of here, but I could, in the nonlinear terms, you get interactions like this, if I were to write all of them here. And this, again, simplified. So this, for instance, a cubic term divided by m Planck times m squared. I restored m Planck in my last answer. I didn't keep it here, but I restored in the final answer because that's the right dimensionality of this term. So many of you know that this is just a cubic Galilean, but it's suppressed by the powers of a λ3 scale that I had on my previous slide. And that λ3 scale is proportional to the second power of m, and because m is small, that λ3 scale is small. And therefore, in your Lagrangian, you have these higher dimensional operators, so to speak, suppressed by small scale. And typically, that gives various types of issues. Even you can trace those issues in cosmological solutions or in black hole solutions which exist in this theory. So as you know, there is a full nonlinear theory of massive gravity, which is entirely defined by the requirement to have 5 degrees of freedom of a massive graviton, as it should, again, according to the representations of the Poincare group. This has nothing to do with Lagrangians or anything else. It's just a symmetry-based consideration that massive graviton in Minkowski space has to have 5 degrees of freedom. And in other spaces, you can also count those degrees of freedom and make sure that they are 5, as long as they smoothly transition to Minkowski space. And that fixes the unique theory, as you know, the terms of which are written here, and many of you have looked at this theory, so I won't spend too much time except to fix my notations that I'll be calling this matrix K, which is composed of the inverse metric G and what's called a fiducial metric made of additional 4 scalar fields. So these are, in this formulation, the theory is fully diffeomorphism invariant, but that is achieved at the expense of having additional 4 scalar field phi a's. That's very similar to doing, let's say, Proca theory for a photon and introducing Stuckelberg fields. So these are Stuckelberg fields. Of course, naively, one would think that we've included, in addition to the tensor, two tensor modes, 2 helicity modes of a tensor, 4 additional ones in these phi's. But the magic of the specific form of the Lagrangian is that precisely there is a constraint which eliminates one of these 4. So there is really 3 that's in addition to the 2 tensor perturbations. So as a result, this theory propagates 5 degrees of freedom on a generic background. So again, very quickly, this is a very brief summary of what many people have done and contributed to in cosmological solutions. I know Emir has given a talk yesterday, and there are many others interesting ones. I will just emphasize basic point that typically this theory and some of its extensions have what's called a self-accelerated solution. That is that without introducing any additional energy momentum tensor, there is a solution of the equations of motion, which at the level of the background either looks identical to de Sitter solution or is very similar to de Sitter solution. In this case, the very first ones in this paper were found where identical background is identical to the de Sitter solutions. But of course, in addition, you have expressions for this Stuckelberg fields phi's that I mentioned. And typically, if you restrict yourself in this minimal theory in which there is only 5 degrees of freedom, the perturbations then are problematic. Some of them become very strongly coupled, or some of them could flip the sign. So you still have 5 degrees of freedom as you should, but some of them start behaving badly, either very strongly coupled or flip the sign and turn into ghosts. But there is no additional ghosts. That was a whole problem that was solved by the construction of this theory. And you can trace those potential issues precisely to those operators that I mentioned. Actually, you can trace those issues to these types of operators being suppressed by low scale, because those operators become, of order of this scale or higher, and kind of change the dispersion relation of the perturbations. That's a simple way to understand it. And hence, for quite some time, we've been looking at extensions of massive gravity in a way that the extensions retain all the good features that the massive gravity has, but perhaps provide some improvement for the perturbations. And a lot of work was done on this again by Mukoyama and Emir Gunguchoglu and Shujang Lin. But there were also very recent interesting papers by the Tabriz group, by Professor Rezai Akbarieh and Shoban Kazempur and Shao and other authors also along the lines of extending this theory and looking for interesting cosmological solutions, which is definitely the interesting direction to explore. So the brief summary before I go to further extension of this theory and advocating for it is that the linearized theory always has 3 additional modes. You can view them as a Namu-Goldstone modes of broken symmetry, because this theory has an additional global symmetry, additional Poincare invariance because of these phi's that I mentioned, and you can view these additional degrees of freedom as Namu-Goldstone bosons of that broken symmetry, and then it guarantees unitary 5 degrees of freedom on nearly Minkowski background. It also guarantees that it's 5 degrees of freedom on any background. However, it may not be weakly coupled degrees of freedom, could be infinitely strongly coupled degrees of freedom, or some of them can flip the signs, and that's because of those higher dimensional operators. The point is that by itself, this theory doesn't seem to be finished in that respect. Of course, it's finished in the respect of if you want to describe just 5 degrees of freedom, that's the theory, period. That's the only one. But if you want to describe, softly high energy behavior, which would be soft and perturbative for reasonable curvatures, then this needs extension. Perhaps the best would be along the lines of obtaining this mass term from some kind of Higgs mechanism, but we don't quite know what that Higgs mechanism is in the case of gravity, and that's the quest we are engaged in. So I would like to tell you about one thought along those lines, one direction that I've been pursuing with my collaborators. I had their names on my first slide. That's Daniel Older, who was my graduate student, and David Pirzkhalava, who was my postdoc at NYU. They are now different places, but these works were done jointly with them. And one idea is to try to enhance the kinetic term of that longitudinal mode. If you remember, I told you that on this slide, I told you that this pi mode here didn't have its own kinetic term. It only acquired one due to mixing, and because of that, the kinetic term that you got was small, and that smallness is precisely the problem of this low scale. So if you manage to have a theory in which that kinetic term is there from the beginning, then perhaps that scale, that strong sampling scale will be higher. And we know examples of that. If you are on ADS background, then the kinetic term for pi is already there to begin with. But this is true actually for any background. This is what the Weinstein mechanism is based. You take a background, whether it's a cosmological background or a black hole background, and because of the curvatures, various types of curvatures, depending on your background, of course, the pi will acquire some additional kinetic term, and that's what resolves the non-perturbative vDVZ discontinuity in the Weinstein mechanism. But here, we don't want to be relying on curvature in 4-dimensional space because we'd like to have general formulation for arbitrary space, starting with Minkowski. And so this observation could be helpful then if the curvature is residing in a higher dimension, if you have higher dimensional space, time, and the curvature is residing in higher dimensions, and 4-dimensional space-time is still flat or nearly flat, and yet the pi mode will get kinetic term just from that curvature in higher dimensional space. So that's the idea. That's quite possible because if you naively try to think about this, and you have space-time with dimensionality capital D, which is 4 plus n. Little n is number of extra dimensions. It could be 1, 2, or more. I'll be talking typically about n equals 1, the 5-dimensional space. And if there is curvature in that 5-dimensional space, then you can convince yourself based on standard Kaluza-Klein type reductions that the pi mode, this capital pi, which would be a higher dimensional analog of the little pi, will necessarily acquire a kinetic term, which can then be inherited in 4 dimensions. So my notations are that m sub capital D is a Planck scale in that 4 plus n dimensional space-time, and m bar is the mass of a graviton in that higher dimensional space-time, to be distinguished from little m without a bar, which is a mass in 4 dimensions. So what that will do is that it will generate an additional kinetic term for pi in the linearized approximation that I talked about. So I'm just giving you an answer here. On the next slide, I'll give you exact nonlinear theory, but I just wanted to zoom your attention on this as to how it works in essence, and then I can talk about full theory. So this is how it works. You get just additional kinetic term for this pi because you have 5th dimensionality or 6th dimensionality in which there is a curvature, and that curvature creates additional kinetic term for this pi mode. And then as long as this coefficient is much bigger than graviton mass to the 4th, which in our world was small, then you are in business because you are increasing the strong coupling scale. And that's a simple argument that you are rescaling your pi by this coefficient, or actually sum of this and this coefficient. And if this is big, this is dominating, so you are rescaling by a big number, and therefore your strong coupling scale goes up. strong coupling energy scale goes up. So the question though is, so what are the new degrees of freedom that are required for this kind of mechanism? And I've introduced whole additional dimension. And as you know, additional dimension comes with Kaluza-Klein modes. So it's not only 1 degree of freedom I've introduced, potentially I've introduced infinite number of degrees of freedom in terms of Kaluza-Klein modes, even though in 5-dimensional or higher dimensional theory, this just could be, one graviton. But from 4-dimensional perspective, this is, well, many or infinity, depending, what the model is. And well, this is consistent with this understanding that I was mentioning in the beginning, that looks like in order to have better high energy behavior in this theory, you need to have additional modes, like the Higgs theory has additional mode, which we call the Higgs. So to make it more concrete, here is a proposal of a full theory. So I'm going to have a 5-dimensional space-time in which the action is the massive gravity in 5 dimensions, the same, DRGT-type massive gravity in 5 dimensions. So M5 stands for the Planck mass in 5 dimensions. It has to be cubed because of the dimensionality of 5. So X stands for our space-time coordinates, and Z is an additional dimension. G bar is 5-dimensional metric. This is a 5 by 5 matrix. R bar is 5-dimensional Ricci scalar. Lambda bar is 5-dimensional cosmological constant, which will be negative, so it will be ADS space. And M bar is a 5-dimensional mass, which is multiplied by the usual terms of massive gravity, all the nonlinear terms of massive gravity, quadratic in K, cubic in K, quartic in K, but now you have one more, because you can write, because epsilon tensor has 5 indices now in 5 dimensions, you can have one more. This is determinant 5. Actually, this is the real determinant in 5 dimensions, because this matrix is 5 by 5, and everything else is, you know how to construct. And the fiducial metric that I'm using here is, again, has Stuckelberg fields. Now there are 5 of them, but this one itself will be anti-de Sitter, or you can obtain this as a dynamical solution as anti-de Sitter if you look at the by gravity. And such fiducial metrics were considered by Hassan and Rosen, and they've shown that, of course, in that case too, you maintain the same number of degrees of freedom as you need to, which is 5 in 4 dimensions, and I believe it's 9 in 5 dimensions. So the total action then is what I wrote on previous slide. That's massive gravity in 5 dimensions, plus massive gravity in 4 dimensions, which is localized on this boundary of 5-dimensional space-time. You can think of it as a brane. And then there are boundary terms, for instance, Gibbons-Hawking boundary terms that you need to include in order to get the right equations of motion in the bulk, but that's just the standard, pretty much standard terms. So that's the action. So 5D massive theory, 4D massive theory, in boundary terms, and the connection between 5D metrics and 4D metrics is as follows. The pullback in general, I'm now considering a coordinate system in which 4-dimensional brane is located at z equals 0 and it's straight, although you can consider any coordinate system that you prefer, but just for simplicity, I chose this. And then the 4-dimensional components of the 5-dimensional metric at z equals 0 is what defines 4-dimensional metric that enters in S4, and likewise for the pullback of 5-dimensional Stuckelberg fields is what defines 4-dimensional Stuckelberg fields, and for the rest is that this 5-dimensional fiducial metric, its pullback is actually Minkowski metric, and that's consistent with this being a solution. So what this slide shows you, next slide, is that what I just described to you in words, it is a consistent solution of that theory. So if the fiducial metric is, let's say this is one parameterization of ADS5, where the coordinates are phi's now, and L is the radius curvature of the ADS space, then you do get as a consistent solution ADS5 for the space-time itself in which that massive gravity propagates. And the next point that's made here briefly is that you don't need to put this by hand. You can obtain this as a dynamical solution if you introduce a second graviton. This would be pi gravity, massive pi gravity in the bulk. And here is a Lagrangian, which is a standard Lagrangian for a massless graviton in the bulk. It has a different Planck scale. And then if you take this Planck scale finite, you can solve, you will obtain this solution, but then you can take this Planck scale, this additional one to infinity, so that this additional massless graviton in the bulk is frozen, so to speak, or decoupled from everybody else because its Planck scale goes to infinity, or its Newton constant goes to 0, and you recover back the theory that I was just talking about, in which there is just a fiducial metric, which is ADS. So you can look at either way. This thing doesn't affect the strong coupling behavior, although it will affect the physics. I mean, the cosmology might be different if you retain this massless graviton and massive one, and that your approach will depend as to what physical problem you would like to address in this context. So that's the full theory. Now, how does that improve over the strongly coupled behavior that I mentioned? Excuse me. You can do the linearized calculations about flux space, because for volume of that brane is Minkowski space actually, unless you put something on it after which it will become cosmological or otherwise, depending what matter you put on it. If you want to have black holes, obviously you can have consider a collapse of matter and so on and so forth. But for the considerations that I'm pursuing, namely the strong coupling scale, I'm looking at the Minkowski space and fluctuations about this. So then it becomes a little involved, because you need to solve for Kaluza-Klein modes, which is not presented here. We recently published a paper for the scalar perturbations in that context. They are very similar what was already done by Dubovsky, Rubakov, and Tinyakov, who looked at massive scalar fields in the Randall-Sundram background. So what you see is that you get one resonance graviton, and then infinite tower of Kaluza-Klein modes, which are low masses are suppressed as they are in the Randall-Sundram context. And you can use that and see how the mechanic that I outlined works. So you indeed get the additional kinetic term for the 5-dimensional longitudinal mode, which is weighted by the curvature of the 5-dimensional space-time. This lambda bar was cosmological constant in 5-dimensional space-time, and it was negative, so that gives the right kinetic term for. I mean, in my notations now it's positive, but it's ADS space. That's what I'm trying to say. And then when you rescale to canonically normalized, this pi sub c refers to canonically normalized. You will see that rescaling now has in it the curvature of 5-dimensional space-time, which is denoted by h bar. And this curvature could be pretty large. Nothing prevents it to be at the God scale, for instance. This is the grand unified theory scale, as long as it's somewhat below the Planck scale, so that you don't encounter all the quantum gravity conversations and stringy modes or anything like that. So this is pretty safe in terms of the description as a classical or effective field theory, a classical theory or effective quantum field theory. And then you can look at the nonlinear interactions like you would in massive gravity. In flat space, those interactions, dominant ones, were coming from this sort of mixing terms. This was shown in this paper long ago, and then you can just very straightforwardly generalize to 5-dimensional space. It has a similar structure, but you will discover that these are not the worst terms. Actually, these start to behave really well after the rescaling that I had on the previous slide. But the worst terms are the ones that don't exist in flat space. These are the terms which in flat space give you total derivatives that we typically ignore here. Because derivatives are covariant derivatives, they don't give you entirely total derivatives. They give you total derivative plus something that's proportional to the commutator of covariant derivatives, which is proportional to the curvature of space. And these are new terms then that you get. But you can evaluate as to what scale those terms are suppressed. And this is somewhat detailed computation, which I'm not showing here. But the answer that you get is that there is an additional suppression. So, that scale grows. That scale grows by a very significant factor. It grows by the ratio of the 5-dimensional curvature divided by graviton mass to the power 2/7. And this curvature, as I said, could be 10 to the 15 GeV, while this is 10 to the minus 42 GeV. So this is a very large factor. So it's much bigger as compared to what the strong coupling scale would have been in just flat in a theory of flat space. And you can then integrate out this 5-dimensional bulk to get 4-dimensional kinetic term for the longitudinal mode, and that has this structure, the square root of D'Alembertian times the Bessel. These are McDonald functions. They are modified Bessel functions, K1, K2 that you know well. And they are functions of the operator of square root of the D'Alembertian. In fact, the poles, you can think of this as inverse propagator. And if you look at this inverse propagator, all poles correspond to this continuum of Kaluza-Klein modes that exist in the theory, but they don't obstruct your 4-dimensional physics too much because they are suppressed. Their wave functions are suppressed on the brane. Similarly, that they are in Randall-Sundram scenario, and why the Randall-Sundram works. That mechanism works here too, but it gives you additional kinetic term. If you expand this for small momenta, it gives you additional kinetic term for pi, and this was the goal to have this. And typically, this is large because this lambda bar is large. And when you incorporate all that knowledge, you will find out that the scale actually goes up very significantly. So this is then the new strong coupling scale. As you see, power of m got replaced by by some power of high-dimensional curvature, which is a very high scale. This is to the same point as I was making before, that there is an enhancement of that scale by the ratio of bulk curvature divided by bulk graviton mass. And in terms of numbers, if you assume that this was the GOT scale, you would have then the strong coupling scale to be MeV as compared to the 10 to the minus 19 MeV. This is like 19 orders of magnitude improvement in the strong coupling scale. And all this without fine-tuning the coefficients of general massive gravity theory. If you fine-tune some of those coefficients, you can get even higher, actually a lot higher than this. But in the most conservative case, you get this. Now, an interesting question that you may ask is, what is the holographic dual of this? Because as you know, when you have ADS5 theory of gravity, there is a holographic dual description. The most rigorous, of course, is the supersymmetric version of it. But since Maldacina's proposal, there have been lots of works on showing that non-supersymmetric versions also have a conjectural description in terms of 4-dimensional conformal field theories. And you may ask that question here as to what that description would be. And there is a peculiarity in that description. And the reason why that peculiarity is that 5-dimensional graviton has now a mass. And that mass immediately translates into the anomalous dimension of the operator to which it couples in the 4-dimensional CFT. And that's the stress tensor. Now, stress tensor, if it has an anomalous dimension, that means that it's not conserved. And this suggests that the 4-dimensional theory is some sort of conformal field theory. You know that because there is still ADS5. The isometry group is the same. It's isomorphic to the conformal group in 4 dimensions. So therefore, it's a conformal field theory. But it's such that it doesn't have the conserved stress tensor. And this indicates that the Lagrangian, 4-dimensional Lagrangian, has a non-local description. And in this paper with Sofia Damokos, in fact, we argued that this should be very similar to what's called unparticled, what Georgia called unparticled. This is one of the versions of the unparticles, in fact. Now, from the 4-dimensional point of view, that looks scary because we don't like to work with non-local theories. They typically come with lots of problems, with unitarity, causality, and so on and so forth. But not in this case. because it has, very nice 5-dimensional classical description. So if there is a difficulty encountered with 4D description, you can always resort to 5D description. But also, I would say that from 4D point of view, the unparticle theories are kind of well defined in terms of their correlation functions, and that was a proposal in particle theory quite some time ago by Georgia, when you could do calculations of lots of amplitudes and properties of particles in those types of unparticle theories. It looks like these massive theories are dual to those unparticle theories, or some of their versions. So the way then you can think of massive graviton from the point of view of that 4-dimensional CFT is that 4-dimensional non-local CFT has a metastable bound state, which is a massive graviton. So that's the picture that emerged from these duality considerations. I have 2 minutes remaining, so I will very quickly go through this slide. That what this discusses is similar construction that I outlined, except that the bulk theory is even more complicated in some ways, because the graviton mass in the bulk theory can be induced by quantum loop corrections. In the theory that I wrote, the advantage was that I just gave you the action, classical action. I just wrote the graviton mass by hands and gave you classical action. And in that theory, already the strong coupling scale went up. Now, the advantage of this theory is that I don't have to write any master by hand. It will be induced by quantum loop corrections. And in that respect, it's better motivated because it explains the origin of that graviton mass. But the disadvantage is, of course, the full Lagrangian is, after full effective Lagrangian is horrendous, although you can write it down in terms of some operators that as we have done in a paper with Daniel and David. But the physics is somewhat simple. You got on the CFT side, on the 4D side, you have 2 CFTs which are disjoint from one another, but at some point then you will couple them together, and that corresponds to 2 ADS spaces from the point of view of massive gravity. One is the physical ADS space, so to speak, in which massive gravity propagates, and the other one is this fiducial one that I was referring to. That's a connection to the previous theory. But due to some specific boundary terms that one introduces in this construction, you can generate the bulk graviton mass. It's a Fritz-Pauli mass, but you will also generate a whole tower of bound states in this theory, and that's what makes it somewhat more complicated, perhaps less attuned to cosmological computations, which are classical computations in which you would like to solve equations of motion. So this is more difficult to solve, but it gives you an example of massive gravity in which actually the strong coupling scale could be raised all the way to the scale of the bulk cosmological constant, which could be the GOT scale, as I said. So a few conclusions. In general, beyond Einstein theories of gravity, these are interesting theories, some of them which have applications to cosmology or late-time universe or early universe. Also, I didn't talk about black holes, but there is a whole interesting physics, as you know, and many of you know about black holes in this context. And typically also, unless if one restricts to the minimal setup, just minimal degrees of freedom, there is a strong coupling problem. But there are extensions now that alleviate that problem somewhat, or raise that strong coupling to a lot higher values, and simultaneously remove, as a result, the vDVZ issue, because those additional modes are not effectively coupled to the 4-dimensional stress tensor anymore because of the same type of rescaling that raised the strong coupling scale. And then there is also a theory that I mentioned in which graviton mass in the 5D ADS space is induced by loop correction. As an effective quantum theory, that's more appealing, but from classical point of view, in terms of practical application, calculation, cosmology, and black holes, this is a little bit more difficult than the one that I presented here, but nevertheless interesting for understanding as to what's going on in this set of theories. Thank you very much for your attention.
Thank you you very much for your excellent presentation. We'll be very happy if you provide us with your presentation file.
Of course, I will send you the file.
Thank you very much. It is very interesting to me that we can find a way to detect these particles, graviton particles in experiments. In this regard, I have two questions. First, how can these particles be produced? For example, in what areas do we expect the density of these particles to be the highest? And exactly what couplings can exist with the standard model particles? The second question is how to identify these particles. That is, it is hoped that some of the energy lost or missing energy in CERN or other detectors is related to these particles. Can you, thank you for your comment on this.
Sure. Yeah, this is a set of all good questions, but many of them. So I will try. I will try some of them. All of them are very important, of course. Let me begin with a minimal setup in which you have only 5 degrees of freedom, let's say. And suppose you decided to explore that theory and look at the consequences of the additional degrees that you have as compared to general relativity. So those would be 3 additional ones. One would be, two additional ones will be helicity 1, and the 5th one will be helicity 0 that I talked about. Now, helicity 1 is not well coupled to stress tensor. It's not coupled in the linearized order because stress tensor is conserved. So that only manifests in nonlinear effects, which are a lot smaller. But helicity 0, of course, it does couple, and there is a whole Weinstein story as to how it gets screened. And if you are in that minimal setup, Weinstein mechanism indeed works observationally. So in our universe, in a classical theory, you won't see too much effect of that, except there will be some small corrections to various observables, and most distinctly probably to the ones that can be measured very precisely, such as perihelion motion of the moon, for instance, will be influenced by that to a certain degree. The lunar trajectory is measured with excruciating accuracy, as you know. And this additional mode will make a correction to the trajectory. The experiment is not at the level at which they can detect that modification, but it is approaching the level in which you would get it could test a similar type of modification in the DGP model, in which it's kind of stronger. So that model could be ruled out, for instance, based on those sorts of considerations. I mean, it's cosmology is a separate story, but this already is a kind of local measurements. But in general, the precision observables in astrophysical settings or planetary settings would be the one to look possibly for those contributions. They are very small. They are very small, but maybe future experiments can detect. Now, better hope, I would say, is in the context of structure formation, because as you know, even if the background is identical to de Sitter or very close to de Sitter, the fluctuations are very different in these theories. You get those extra modes precisely, and even when the Weinstein mechanism is operating at the let's say nonlinear scales, you still can look at the linear scales in the universe, a lot bigger than the clusters of galaxies, or quasi-linear scales as you form clusters. And at those scales, the Weinstein mechanism is not operative because curvatures are not that high. That's a simple reason to understand why it's not that operative. And therefore, there will be significant contribution competing with gravity due to the helicity 0 mode. So structure will be forming differently. It will be forming, it will be forming faster. Collapse will be taking faster because if the helicity 0 mode is a healthy spin 0 particle, that will provide additional attraction for structure formation, and people have worked on that. In DGP, on the self-accelerated branch, which has a ghost, actually, that pi is a ghost. It's a repulsion, so it prevents structure to form as fast as in general relativity. So that's one of the issues there. But here it will be attraction, and that's a place which one can look, but again, it requires some precise data from cosmology, which cosmology is approaching, obviously, with the subsequent measurements. Now, if we extend the theory in various ways, then it depends on extensions, of course. You know, in your extension, you had fuzzy dilatons and you had Galileons, so those are all very interesting approaches, and you can think of again looking at small effects either due to structure formation. It depends how, again, it depends how it couples to matter and so on and so forth. These are little model dependent aspects. That doesn't but that doesn't mean to say that they're not interesting. They are interesting because in any given model you will have similar consequences either at smaller scales, let's say solar system scales, or at large scales. I'm sorry, I meant to say and or at large scales, at the cosmological scales, consequences of similar nature related to these extra modes, mediating additional forces, essentially. Now, in terms of radiation, when I talked about this embedding into five-dimensional theory, I think one part of your question was that you have now, you know, additional Kaluza-Klein modes, actually infinite number of them, and how about, you know, losing energy into those modes? That is absolutely happening. You would lose energy into extra space, but that's a tiny effect for the same reason that it is a tiny effect in the Randall-Sundram scenario. So what happens is that naively, if you look at the Randall-Sundram scenario or this scenario, naively one would think that it's immediately ruled out because there is no gap in Kaluza-Klein spectrum. It's continuous. And then you look at very, very light modes and you'd say, well, these are as light or almost as light as massless graviton. So therefore they must be competing with you know, four-dimensional Newtonian theory already, let alone general relativity. But the interesting phenomena, which is actually why Randall-Sundram is so famous, is that those low energy modes, they all get suppressed. They get additional suppression on the brane in four-dimensional space. So they don't couple effectively with four-dimensional observers. Of course, it's a matter of calculation, and one has to be very careful and calculate because still there is infinite number of them. They are very weakly coupled, but there is infinite number of them, and it's not clear which effect wins until you calculate. And then you calculate, and you see that these are smaller corrections, although power law corrections, not exponential like in standard Kaluza-Klein construction. Here they are power law corrections, but they are small corrections until you reach the scale of the order of the curvature of the bulk, which in those scenarios are typically, you know, God scale or, you know, way above TV scales, for instance, and therefore your observers have really small corrections. I hope I captured some of your.
Thank you for your excellent explanation. And any question? Right.
Yeah. So with the yeah, thank you for that question. It's an important one for sure. With the advancement of this massive gravity, when you can write down, you know, theory with 5 degrees of freedom, then you can overcome of all those no-go theorems, even with bi-gravity or multi-gravity. You can just couple then massless gravitons, additional massless gravitons to this one, or other massive gravitons to this one in a consistent way. So let's talk about bi-gravity because it's a simpler one. So you can couple just one additional massless graviton to this one in a standard way. You just introduce, you know, general relativity for the massless one. In fact, I had it on one of my slides, some version of it. This one, I mean, it's a. So on previous slide I showed, on this one I talked about this being a fiducial metric which was put by hand. But if you make it dynamical, which you can, by adding to the action this action, then you got bi-gravity. One is massless, another one is massive. Massless will have 2 degrees of freedom, massive will have 5 degrees of freedom. And then this Yeah, so here is massless, and then you can have one. Oh, you want to have more than one? Yeah. Got it. I believe that's possible. I believe if you look at the paper by Kurt Hinterbichler and Rachel Rosen, they've written Vierbein formulations. They've written massive gravity in Vierbein formulations. And in that formulation, these terms are simply looking. You can have Vierbein, E1, let's say E2, E3. So you can have a multi-graviton theory by combining those Vierbeins into the forms. So you need, in any dimensionality, let's say in 4-dimensionality, you got to construct a 4 form, and you can construct that 4 form with various combinations of your Vierbeins, of exterior products of the Vierbeins. So that gives you a multi-graviton theory in which one is massless, other ones are massive. And I'm not 100% sure that those masses can be different, but I don't see a reason why not. That part I don't remember, but you can look at the paper and see. I believe it could be different masses because you put different coefficients in front of different terms, and when you diagonalize, I would expect you can have one massless and let's say 2 or 3 massive different masses. Yes.
Thank you. Any question? Thank you very much, Professor Gabadadze. And the next speaker is Anania Mukherjee from Massachusetts Lowell.
Thank you all.
Thank you.